Stars don't live forever. Even our sun has a limited lifetime. It's been around for about 5 billion years, and it's got another 5 billion to go. But what happens when it dies? Small stars like our sun will start to grow. They'll expand as new types of fusion occur right at the center of the star. So our sun, when it gets old, will puff out into what we call a red giant, at which time it'll grow so large that it will eat the inner planets. It'll first eat Mercury, then Venus, then the Earth. And once it gets that large, the gravity of the sun is not really strong enough to hold it together anymore. So it'll just kind of let its outer layers drift off into space. And it'll become something known as a planetary nebula, a rather beautiful display of colors of gas drifting into space with a very solid white dwarf sitting at the center, a white dwarf made mostly out of carbon. But stars much bigger than our sun aren't nearly as mundane when they die. They are quite aggressive. You've probably heard of something called supernova before. And they're what happen to stars which are about 8 times more massive than our sun. You see, very big stars have a lot of energy they need to deal with and keep balance. So when fusion reaches iron, the end point of all fusion energy in the center of those stars, they're now under the complete control of gravity. Because in general, stars are being held up by gravity pulling them down and energy from fusion pushing out. But if you take away the energy from fusion, gravity will just simply pull everything down. For these very big stars, 8 times the mass of the sun, when their fusion stops, the outer layers all begin to collapse down until they hit the center of the star. And depending on how massive the star is, 2 different things could happen. If the star's reasonably large, so say between 8 and say 15 times the mass of the sun, the center, the very core of that star will compress and become something known as a neutron star. And this neutron star doesn't want to go anywhere. It's happy being the size it is. And it sees all of this rushing material coming down, and it collides onto the surface of the neutron star. At that point, it all pretty much just ricochets off. And the explosion from a supernova is just material bouncing off the core of this neutron star. So that's what these massive explosions are, just immense collapse and then bounce back of lots of stellar material. So these supernovae are known as core collapse supernovae. And it's pretty easy to see why. The core of the star stops working, collapses down, and everything else comes down after it. They're very bright things. They can be billions of times brighter than the sun quite easily. And there's lots of interesting physics in the way that they explode. But in general, astronomers are more interested in another type of supernova, called a type 1a supernova. Now these have a completely different mechanism as to how they actually explode, and it's quite interesting. See, type 1a supernova come from binary star systems, so you have 2 stars orbiting one another. But in this binary, one of the stars has lived out its lifetime and it's now a white dwarf, so one of those carbon stars that our sun will turn into. But there's the binary companion orbiting around this white dwarf. And the material from the companion eventually will start falling onto the white dwarf. The gravitational pull of the white dwarf will stream material off that star and pull it onto itself. So it's cannibalizing its sibling. And over time, this white dwarf gets more and more massive until it reaches a very critical stage. If you pile more and more mass onto a white dwarf, you can ignite burning inside the core. And once that happens, you undergo a nuclear explosion, which is extremely bright and can easily outshine galaxies. These type 1a supernovae are around 5 billion times brighter than our sun, so they're incredibly bright objects. But the very interesting thing with this type of supernova is that the way in which they're produced is very standard. They need a very precise amount of mass that will set them over the edge to explosion. It's often called the Chandrasekhar limit, but there's ongoing research into actually how these things blow up in the first place. But the important thing is, if this star blows up in a very similar way, you can characterize how bright you expect it to be. And with telescopes on the ground, you can measure how bright it appears to you. So like with this torch, if it's close to the camera, it seems very bright. But if I take it away from the camera, it looks fainter. Now it's not that the torch has changed in brightness, it's that the distance between the camera and the torch has increased, so the light is being spread over a greater area and not as much of it is falling onto the camera. Now the exact same thing happens with these supernovae. If we know how bright they should be and measure how bright they are, we can treat them as kind of a standard candle, it's called. We can measure distances in the universe with this object. So there's another property which astronomers like to measure with the supernova, and everything else in space in general. There's something called redshift. So that's a measure of how much the spectrum, the rainbow of light that's being emitted by the object, gets shifted to the red end of the spectrum. Now this is to do with the relative motion between us and that object. Now if you combine the measurements of distance from your Type 1a supernova and redshift from the spectrum you gathered, you're able to tell something about the universe itself. If you measure a whole bunch of different Type 1a supernovae out into the universe with different redshifts, you can see how the expansion of the universe changes over time. And what astronomers had found is that the universe accelerates in its expansion, which is quite bizarre and not what people expected to find at the time. You see, if the universe started from a Big Bang, you'd expect the energy of the Big Bang to give it a kick and it to start expanding. Over time, gravity will soon take control of the universe and pull it all back down to a singularity. Much the same as if I jump, I go up for a bit, and then I come straight back down. So the observation that the universe was accelerating in its expansion, that further away objects were moving faster and faster away from us based off these supernova measurements, we were able to tell that we live in an accelerating universe. And that, of course, gave rise to the notion of dark energy, that there's something in the universe which is pushing against gravity, making it accelerate in its expansion. Now, dark energy is a code word for we have no idea what this thing could be. So it could be a unique new energy that we haven't discovered yet, or it could be something else entirely, just some type of physics we're not using properly. So we can use the ends of stars' lives as very interesting tools to probe physics and some of the fundamental physics of reality. In general, there's about 50 supernovae that go off every second throughout the universe. But we've only measured a handful of those supernovae. But with that handful, we've discovered some pretty incredible things.